All right, so let's just jump right in. You've seen the headlines, right? We are in the middle of a full-blown AI gold rush. It feels like this incredible software revolution is changing literally everything. But the real story, the one we're going to dig into today, isn't about the code. Nope, it's about the physical stuff. We're talking silicon, metal, electricity, and a massive looming crisis in the hardware that's supposed to power this whole thing. So, to really wrap your head around the scale of this problem, just look at this number. 5 trillion. That's not a typo. That's how many parameters the experts think a cutting-edge AI model will have by 2025. And to put that into perspective, think back to just 2018. We were excited about models with less than a billion parameters. This isn't just a step up. It's a completely different universe of complexity. It's a straight-up explosion.
And that right there, that brings us to the core problem we're tackling in this explainer. You know, our AI dreams, our ambitions, they're skyrocketing. But the hardware? It's like it's stuck in traffic, desperately trying to keep up. So it begs the question, right? What in the world does a computer even look like that can handle that kind of raw power?
So to try and solve this massive challenge, engineers are in this absolutely frantic race. They're designing these super specialized chips, which they call accelerators. But here's the fascinating part. There's no single right answer. It's not one size fits all. Instead, what we're seeing is a battle of ideas, almost like different philosophies on how to build the perfect AI brain. Each one has its own blueprint, its own set of trade-offs.
Okay, this table really lays out the whole battlefield for us. You've got the ones we all know, right? The GPUs for NVIDIA. They're kind of like the Swiss Army knives, super flexible, the workhorses of the industry. But then you get into the really specialized stuff, like Google's TPUs. They are laser-focused on being incredibly efficient at the one type of math AI loves, these big matrix calculations. And then you have the wild ones. Cerebras is literally building a single chip the size of a dinner plate, just for mind-boggling parallelism. Or you've got Grok's LPU, which is built for one thing and one thing only: pure, unadulterated, predictable speed. The big takeaway here, looking at all these strengths and weaknesses, is that there's no magic bullet. The best chip, it totally depends on what you're trying to do.
And this gets to the fundamental trade-off. It's the big choice every single hardware designer has to make. Are you optimizing for speed, or are you optimizing for scale? Think of it this way. On one side, you have something like gross chip. Its whole goal is what's called low latency. That just means getting an answer to one person as fast as humanly possible. We're talking blink of an eye fast. Perfect for a chatbot, right? But on the other side, you have high throughput beasts like NVIDIA's latest. They're designed to process a crazy amount of data for tons of users all at once. The key is, you can't be the best at both. You have to pick a lane. But okay, let's say you've picked your champion. You've got the perfect processor. Well, there's a deeper, kind of hidden crisis lurking right inside the chip. Because here's the thing, the fastest processor in the world is completely useless if it can't get data fast enough. It's like having a Formula One car with an empty gas tank. And that data, that fuel, it comes from this super fast on-chip memory called SRAM. And the problem? SRAM has hit a brick wall. Hard. Yeah, this quote it nails the feeling of dread in the industry right now. For decades, we lived in this magical world where we could just reliably shrink everything on a chip year after year. That included the memory. But that party is over. The laws of physics are finally calling our bluff. The magic trick we used to cram more and more memory into smaller and smaller spaces, it just isn't working anymore. And if you want to see what that looks like in the real world, check out this chart. This shows the size of a single tiny memory cell on two back-to-back generations of chips from TSMC, and these guys are the best in the business. See what's happening? Look at those bars. They're the same height. From one major generation to the next, the fundamental building block of memory, it didn't shrink at all. It just stopped, flatlined. So what's the big deal? Well, here's the consequence. The brain part of the chip, the logic, it's still shrinking, it's still getting smaller and more efficient, but the memory part is staying the same size. So you get this crazy imbalance. The memory starts hogging all the space on the chip, guzzling power, and making the whole thing way more expensive. It creates this terrible traffic jam, a bottleneck right there on the silicon that could make the next generation of AI chips just too slow and too expensive to even build. Okay, so things are looking a little bleak, right? We have a problem with what kind of processor to build and a fundamental physics problem with memory. But just when it seems like we're stuck, a really clever solution is starting to take hold. And the brilliant part is, it doesn't even try to fix the memory chip itself. Instead, it completely changes the rules for how a computer thinks about and accesses its memory. It's called CXL, which stands for Compute Express Link. And the best way to think about it is, imagine a universal power strip, but for memory, a super fast one. It's an open industry standard, which is key because that means everyone can use it. And it basically creates this high-speed highway, a highway that lets all the different kinds of processors, your CPUs, your GPUs, all your AI chips, reach out and grab from one giant shared pool of memory whenever they want. So here's how it actually works and why it's so smart. Right now, in a typical data center, you have tons and tons of memory that's just sitting there, doing nothing. It's trapped inside one server dedicated to one CPU that might not even be using it. It's incredibly wasteful. What CXL does is it lets you find all that stranded, idle memory and liberate it. You pull it all together into this one massive shared resource. Then you can dish it out on the fly to whichever processor is screaming for it at that exact second. It's just a genius way to get rid of all that waste. And the bottom line impact of this? It is absolutely staggering. Just by letting data centers use the memory they already have more efficiently, CXL can slash the cost for every gigabyte of memory by around 55%. Let that sink in. This isn't some tiny, incremental improvement. This is a total game changer for the economics of AI. It makes building these massive systems so much more feasible. So, we've got these new chip designs, we have this new way of connecting memory. What does this all mean for the AI brain of the future? What's it actually going to look like? Well, all the signs are pointing in one direction. Systems are going to get way more specialized, way more complex, and more intricately connected than ever before. So there are a few big trends we're seeing emerge. First, this idea of heterogeneous memory. That's just a fancy way of saying we'll mix and match different kinds of memory to get the perfect blend of speed and affordability. Then we're seeing chips with hardware built specifically to run these new mixture of experts models, which you can think of as a team of little specialist AIs all working together. We're even seeing dedicated hardware engines to tackle a notorious memory guzzler in large language models called the KV cache. That's the part that remembers your conversation. And of course, you can't forget security. We need new defenses against these wild new attacks like Volt Boot, where hackers can literally mess with the chip's power to steal data right off the silicon. Crazy stuff. And all of this leaves us with one big, final question to think about. The dreams we have for AI, what we want it to do, that ambition is pretty much limitless. The real question is whether the physical stuff, the hardware we build, can actually keep up. So will our silicon be the bottleneck that ultimately chokes this revolution? Or will the kind of brilliant, out-of-the-box engineering we've talked about today be the thing that unlocks a future we can't even begin to imagine?